So what is the combined gas law? It's a combination of the laws that we've been talking about. It's usually a combination of Boyle's, Charles, and Gay-Lussac's law. So pressure, volume, and temperature. But occasionally it can also include Avogadro's law. If you have that version, you can actually derive all of the laws from it. This is the version you're going to see on the test that's going to be the most useful to you. P1V1 over T1 equals P2V2 over T2. And it really relates all of the laws to each other. It relates pressure, volume, and temperature all to each other. A couple things to remind ourselves of. Standard temperature and pressure. What does that mean? Well, these are the standard or usual conditions when setting up experiments. It's actually just kind of a convention that standard temperature is 273 Kelvin or 0 degrees Celsius. This will be given to you on the test, what standard temperature and pressure are, but you want to be aware of it. You want to know what we mean when we say standard temperature or standard pressure. Okay, standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere, which can be converted to 273 Kelvin can be converted to 0 degrees Celsius. 1 atmosphere can be converted. It's equal to 760 millimeters of mercury or torr, and it's also equal to 101.3 kilopascals. We could do a couple example problems where we are just having to apply a change to all three of those variables down here. So I have a gas at 110 kilopascals in 30.0 degrees Celsius. It fills a flexible container with an initial volume of 2.00 liters. If the temperature is raised to 80 degrees Celsius and the pressure is increased to 440 kilopascals, what's the new volume? Okay, there's a lot going on here, so this is definitely a time we're going to want to label our variables. Now our equation is P1V1 over T1 equals P2V2 over T2. So we've got all three variables. P1, V1, T1. And then I'm also going to have P2, V2, T2. P1 was kilopascals, 110 kilopascals. 30.0 degrees Celsius was our starting temperature. Remember, if you have degrees Celsius, we need to add 273. And that's going to give us 303 Kelvin. All right. We also have an initial volume, our starting volume, at 2.00 liters. And now we want to look at our change. What is the new pressure, volume, and temperature? Well, the new pressure is 440 kilopascals. We want to check and make sure our units match. They do here, kilopascal, kilopascal. V2, what's the new volume? That's what I'm looking for, the new volume. So this is unknown, but I know that the units are going to be liters because that's the units I have up here. And then T2 is 80.0 degrees Celsius. And we're going to add 273 in order to get Kelvin. I have 353.0 Kelvin. Now we are going to solve for this. P1 V1 over T1 equals P2 V2 over T2. So I have 110 times 2.00 over 303 equals, and then we have 440 times V2 over 353. There's a lot going on in this, so it may be the easiest thing to do for you to just cross multiply. You may have another way you'd like to solve this, but with this much going on, that might be a useful tool. So I have 303.0 times 440 times V2 equals 110 times 2.00 times 353.0. If I want to get V2 by itself, I'm going to have to divide both sides by 303 and 440. Now I want to caution you, if you're doing this all in one step in your calculator, make sure that you put double parentheses down here so that you don't make a mistake. Your calculator needs to understand what you mean, so make sure you're following order of operations correctly. Both of the things in the denominator need to be enclosed in parentheses to get the right answer. But if I divide this, I'm canceling everything out. I end up with just V2 equals, and if I do my math correctly, I should get 0.58. Yeah, and that's to two significant figures, so 0.58 liters. Okay, let's look at our next problem down here. At STP, a sample of gas occupies 30.0 milliliters. And you notice it says at STP. Remember, that is temperature and pressure. Okay, now I'm going to erase that. But STP, that's temperature and pressure. So we could go ahead and start by writing P1, V1, T1 at standard pressure. That's 1 atmosphere, or what are the other units that we have in this? Well, it doesn't tell us. What will be the gas pressure inside the container? So I'm just going to go with our standard units of 1.00 atmospheres. Our volume, our initial volume is 30.0 milliliters. And our temperature, our initial temperature is standard. Standard temperature is 273 Kelvin. All right, that's our starting values. It says if the temperature is increased to 30.0 degrees Celsius and the entire gas sample is transferred to a 20.0 milliliter container, what will be the pressure inside the container? So our temperature is, instead of being 273, it's going to be 30 degrees Celsius. P2 is what I'm looking for. V2 is 20.0 milliliters. T2 is 30.0 degrees Celsius. And I need to add 273 because I need it in Kelvin. 30 plus 273 will give me 303 Kelvin. All right, and now we could go ahead and solve this problem. P1 V1 over T1 equals P2 V2 over T2. So I have 1.00 times 30.0 divided by 273 equals, our unknown is P2 times 20.0 divided by 303. So if I want to solve for this, I end up with, I could cross multiply. and I'll get 273 times 2.00 times P2 equals 1.00 times 30.0 times 303.0. And if I wanted to solve for this, I'm going to divide both sides by 273 and 2. Or you could just multiply those numbers together, find out what that would be, and divide by that. Either way works. And you do that on both sides. If I put that in my calculator, I end up with 16.6 atmospheres, I believe is what we were looking for. Yes, 16.6 atmospheres as our second pressure. Okay, we got one more example where we're applying this formula in this way, and then we're going to learn a little trick to come up with all the other equations, which is going to be really useful and a quick trick for you to use on the test. All right, it tells us a sample of air in syringe exerts a pressure of 1.02 atmospheres at a temperature of 22.0 degrees Celsius. The syringe is placed in boiling water bath at 100.0 degrees Celsius, so our temperature will change to 100 degrees Celsius, and the volume expanded. The pressure of the air is increased to 1.23 atmospheres by pushing the plunger in. The new volume is 0.224 milliliters. What was the original volume of the air? Now this sounds kind of tricky. Original volume, that's V1. So we need to recognize we're looking for V1. Okay, so P1, V1. V1 is what I'm looking for. T1. And then we're going to have P2, V2, and T2. All right, our initial pressure was 1.02 atmospheres. The initial temperature was 22.0 degrees Celsius. Plus 273 because we want Kelvin. All right, P2 is 1.23 atmospheres. It's over here. And V2 is 0.224 milliliters. Then T2 finally is 100 degrees Celsius, 100.0 degrees Celsius. Plus 273, which gives us 373 Kelvin. Now we could set up our equation to solve. I end up with P1 V1 over T1 equals P2 V2 over T2. I'm going to have 1.02 times V1 over 295.0 equals P2 is 1.23 times V2, which is 0.224, over T2, which is 373. Then we just want to cross multiply to rearrange and solve for V. So I end up with 1.02 times 373 times V1 equals 295 times 1.23 times 0.224. All right, and You may want to just go ahead and do 1.02 times 373 so that you know what that is. It's 380.5, 380.46. So if I wanted to multiply these two numbers together, what I get is 380.46. So you could maybe just divide 380.46. That's the same thing as dividing by both 1.02 and 373.0. I'm just showing you this is another way you could think about this problem. Same thing that we did in the last couple problems, but this might be easier for you so you don't have to worry about whether you're plugging it in the calculator, right? Just have your denominator as one number. So when I do that, this does cancel out because 1.02 times 373 does equal 380.46. So I end up with V1 equals 0.214. And that would be milliliters. Original volume was 0.214 milliliters.